We have a root directory with some files inside it. Operations like listing, reading, and deleting might seem trivial to us. After all, we do them every day. But under the hood, they are anything but trivial. To start with something interesting, did you know that file metadata like timestamps and permissions are not stored with the file's content itself? And no, this is not a design accident. There are very strong reasons for doing this. Also, the metadata stored in the files does not include file names. File names live somewhere else entirely. Things get even more chaotic when we realize that directories themselves are just special files whose contents describe their children. Yes, directories are files too, just with a very opinionated structure. In this video, we'll explore file systems and their internals. And then, we'll zoom in on what actually happens when we delete a file. To begin with, let's quickly skim through the layout of a very popular open source file system, ext4. Don't worry, we don't need to stress over every tiny detail here. ext4 reserves some initial sectors that can be used by bootloaders, but the file system itself is not responsible for loading the operating system. So we'll ignore that part. What we do care about are block groups, because that's where the files and directories we interact with actually live. If we look inside a block group, it's divided into multiple regions. Again, we don't need to obsess over all of them. The most interesting ones for us are the data blocks, which store the actual bytes of file contents. The inode table, which stores metadata about files such as ownership, permissions, and timestamps. The inode bitmap, which tracks which inode numbers are free or allocated. And the block bitmap, which does the same thing for data blocks. There are also structures like the group descriptor and superblock that store metadata about the file system itself. Extremely important, but not today's problem. This overview is just to introduce two key concepts we'll keep coming back to: data blocks, which store raw file data, and inodes, which store metadata about files. At this level, files and directories are treated uniformly. Both are represented by inodes pointing to data blocks. Alright, time to actually get our hands dirty. I'll create a file called file.txt and then I'll fire up debug.fs, which lets us inspect file system internals directly. Note that I'm using the partition where this file actually resides, which might be different on your system. First, let's look at the contents of the root directory where we created file.txt. We see file.txt along with dot and dot, which represent the current directory and the parent directory. You'll also notice some numbers before the names. Those are inode numbers. Remember the inode table we talked about earlier? These numbers are references into that table. We could see this information using ls as well. But let's go a level deeper and inspect what's actually stored in the inode table. For that, we can use the stats command in debug.fs. I'll pass the inode number corresponding to file.txt, and there we go. We can see all the metadata stored in the inode: file type, permissions, flags, timestamps, and a bunch of other fields. What's interesting here is that the file type is regular, meaning this is a regular file, and we also see extents, which describe the ranges of contiguous data blocks where the file's contents live. Extents reduce fragmentation and make sequential I/O much faster, which is why modern file systems love them. If we dump the data blocks referenced by these extents, we can actually see the raw contents of the file. Yes, the exact bytes. Still feels slightly magical. Now, let's do the same thing for the inode number corresponding to the current directory. This time, the type is directory, and the metadata reflects that. If we dump the data block for this inode, we see what looks like random bytes. But of course, it's not random at all. Each directory entry has a defined structure. The first 4 bytes are the inode number, stored in little endian format. The next 2 bytes are the record length, which tells us how many bytes this directory entry occupies, so the file system knows where the next entry starts. Then, we have 1 byte for the name length, followed by 1 byte for the file type, In this case, 2, meaning directory. Finally, we have the file name itself, which here is dot for the current directory. We can continue decoding entries the same way to find the parent directory and file.txt, which is of type regular file. Notice how the inode numbers match exactly what we saw earlier using ls. At this point, you now know how ls works internally. It simply reads directory entries and formats them nicely for humans. No magic involved. Now that we understand the structure a bit better, let's delete the file. After running rm, if we dump the directory again, we see that file.txt is gone, and only dot and dot dot remain. This tells us that the deletion operation removed the directory entry for file.txt. Since the directory no longer references that inode, the operating system can no longer locate the file via the file system namespace. But here's the fun part. We remember the data block number that belonged to file.txt. If we dump that block directly, we can still see the contents of the file. Even if we inspect the inode, chances are it still looks mostly intact. Wait, wasn't RM supposed to delete the file? What actually happened is this. Deleting a file does not erase its data. Instead, the directory entry pointing to the inode is removed. The inode and its data blocks are marked as free for reuse. But the actual bytes are left untouched until something else overwrites them. This is why data recovery tools work. The file system simply forgets where the data was. And the reason file systems do this is performance. Unlinking a directory entry is extremely fast. Overriding potentially large files with zeros every time would be painfully slow. Also, separating metadata from data allows inodes, which are fixed-size structures, to be scanned and managed efficiently without jumping all over the disk. Now, things get more interesting when we ask, what if multiple directories point to the same file using hard links? That sounds chaotic, but thankfully, the file system has answers. Sneak peek, link counts are about to save the day. But before we go there, if you enjoy diving deep into computer science concepts like this, you'll probably love Brilliant. Brilliant helps you excel in math and computer science with visual, interactive problem solving and personalized practice, a method that research has shown to be far more powerful than watching lectures. It has a perfect mix of interactive problems, motivating challenges, and encouragement to keep you moving forward. Each lesson is designed to sharpen your intuition and strengthen problem-solving skills step by step. You will build genuine understanding and reach serious learning goals. To learn for free on Brilliant for a full 30 days, go to brilliant.org/premature optimization, scan the QR code on screen, or click on the link in the description. Brilliant has also given our viewers 20% off on annual premium subscription, which gives you unlimited daily access to everything on Brilliant. Let's come back to the deletion experiment, but this time using strace. Strace shows us the system calls a program makes. I'll run rm under strace and filter out the boring stuff. We can see the unlinked system call being invoked. It's passed with fdcwd, which refers to the current working directory, the file path, and a flag value of 0, meaning this is a regular file, not a directory. The return value is 0, which means the deletion succeeded. To go deeper, we can follow this call into the Linux kernel source. Starting from the system call table, we find unlinked defined, which takes the directory file descriptor, a path name, and flags. After some checks, the call eventually leads us to do unlinked. Here, the kernel locates the parent directory, acquires the necessary locks, yes, locks, because concurrency is fun, and then calls VFS unlink. The VFS, or Virtual File System Layer, is the Linux's abstraction that allows it to support multiple file systems seamlessly. VFS unlink dispatches the call to the file system's specific implementation. In our case, that means ext4 unlink, which eventually resolves to the internal ext4 unlink logic. Inside ext4, the directory entry is searched for and removed. Journaling is performed so the file system can recover safely if the system crashes mid-operation. Timestamps are updated and the inode is marked dirty. Then the inode's link count is decremented. If the link count is still greater than 0, nothing more happens, because some directory still references this inode. If the link count reaches 0, inode is added to the orphan list. This list exists so ext4 can safely clean up inodes during crash recovery or once the last reference is truly gone. Notice what we don't do here. We never touch the data blocks themselves. That's why the data was still there. So let's revisit deletion with a concrete example. Suppose we have two directories, root and fruit, both containing hard links to the same file, a.txt. If we delete a.txt from fruit, the directory entry is removed from fruit and the inode's link count drops from 2 to 1. The inode and data blocks remain fully valid. If we then delete a.txt from fruit as well, the directory entry is removed. The link count drops to 0 and the inode becomes orphaned. At this point, the file system marks the inode and its data blocks as free for reuse. Eventually, future writes will override that space, and only then is the data truly gone. Thank you so much for watching, and I hope you learned something new from this video.